Alright, so we just saw in the last video how to retrieve the copy number of a volume with this command we're placing in the stepping action. So I'm just going to point out, from the last one, this was previous get pre-step point, but now I've just changed it to get post-step point. So you might remember that when we were printing out the copy number ID, because we had the pre-step, we wouldn't get the copy ID printed out except when we exited the volume. So when the boundary of the track was between the two volumes, and since we got the pre, then when it exited, it was asking for the pre-step. And since energy deposition is associated with the post-step, I've just changed it to post-step. So when we're getting energy deposition on the step, when we check for the copy ID, then we're actually getting the copy ID for that energy deposition. Hopefully, because sometimes Geant can do a bit funny, unintuitive things when it comes to certain things when you're accessing tracks and copy IDs. So hopefully I've now got it set up right. So remember what we wanted to do was shoot some radiation field and then just score the energy deposition in those different pixels. So I'm just quickly going to show a method that I think I showed in a previous video for scoring the mean kinetic energy, I believe. But what I'm going to do is just a simple array, and for each pixel I'm going to just have keep track of the energy deposition for each pixel in an array. So let's just make an array. So let's call it px for pixel energy deposition, and we'll just be bad and hard code it. So in our stepping action header, we've just initialized this px and if we go back to the .cc file, then in our constructor of the class, we'll initialize it. So let's just go have a for loop and G4 int 0. Oh, I didn't call it anything. It's called pxid equals 0 and pxid is less than 9. pxid plus plus, and all we're doing is we're going to initialize all the values in this array to be 0. So if we didn't do this, then each element of this array, which will hold 9 values, then it'll just, if you try to add a value to this array without initializing it, then it'll just take in some random memory value, whatever is stored in the memory. So this will probably be just junk memory. So you'll be adding something to the junk, so your whole value will be out of whack. So we need to initialize everything to 0. So we're just ensuring that our pixel is 0. And while we're doing a for loop, we're going to, at the end, in the destructor of the stepping action, so at the end of the simulation, when the simulation's deleting all the classes and cleaning up the memory, then we're going to output the dose. So let's say G4 cout edep in vol. Whoops, didn't anything. Invol pxid is equal to. Whoops, and I didn't actually change that. So to change the element of array, make sure I put the for loop variable, and I don't want it to be equal to 0, I just want to output it, but I'll actually specify the unit, so I want to output it in MEV, and let's just close that off. So pretty sure previously we went through this technique of our post and pre-volume, and we could store energy deposition or retrieve quantities, but only when it enters that volume. So this time we'll go, what did I call the volume? So I'm going to get the physical volume name of our pixel or detector, and since it's phys_px, we'll put that there. So whenever the post volume is equal to phys_px, then we want to actually retrieve the copy number, and we want to score the energy deposition in the array, which I've already forgotten, px_edep. So where are we? So px and what's the variable? So whoops, oh man, plus equals, and I've already got the edep command. Right, so I'll describe this shortly. So what I'm doing is, as the the track's going through our world, checking every post step, whether it's in the volume phys_px, so that's our pixels or our detectors, our repeated detector volumes. And if it is this volume, then we actually want to retrieve its copy number. And once we have that copy number, remember this will be between 0 and 8, then once we have that, we can add the energy being deposited in the step into our pixel edep array, and this should work. And actually, let's also add the energy deposited. So let's go edep_s is equal to edep_s, and let's also output how much energy has currently been deposited in each pixel. So let's go edep in pixel, and we'll just print out the copy ID. So edep in pixel x equals pixel edep, and let's force that to be MEV, and let's print that out. And let's just compile that and see if that's happy with us. So far so good. Let's just run it and shoot a Geant4 to make sure it's not completely useless. So let's just shoot a beam. Make sure that's printing out what we want it to. So where were we shooting? Oh, we're just back in the center, right? So starts at our 0030, hits the pixel at -25 in the Z millimeters, and then copy number 4 and 0. So that looks good. So let's actually just go to viz.mac, since I was having fun with it, and let's just quickly change the Geant4. Where's my Geant4? Or do I not specify Geant4? Oh, I guess I never called it. So let's just quickly add the command for the particle type. So remember, by default, the Geant will just shoot a Geantino if you don't specify what particle, but I'll now tell it to shoot a electron. And so let's just shoot the beam again, but now we're shooting a 6 MeV electron. So run beam on 1. And remember, this is a 5 centimeters squared, so it took quite a few steps in the detector, it looks. So it actually stopped in it, it appears. Yeah, it looks like it's stopped in the detector or pixel. So we've actually got quite a few steps. So this is our first one, parent ID is 0. So starts in our fizz box, so our white volume, which is wireframe, so just this black here. So then we're still in the fizz box, so we enter the pixel here, and we get a copy number of 4, and how much energy deposited we had in it, and 0.197, and 197's there. 0197, and then it increments the dose in that pixel, and then we add 1.3 e to the minus 5, so a lot less. Then we increase a bit more and more and more. So far so good. So let's just exit this, and you can see once we exit the visualization, we get the destructor outputted. So we'll just shoot the pixel, and we saw 4.6 MeV, which makes sense since we shot a 6 MeV beam and lost a bit of energy before entering the pixel. So about 5 MeV is about what we'd expect. So now let's just run in batch mode instead. So I'm gonna increase the beam. So what's our spacing? We're 30 by 30 all ups, since we've got 3 by 3 array, and we've got 3 by 3 intent spacing. So let's make this this is a half volume here. So let's go 20. Yeah, 20. And 6 MeV is good. And I'll change this to, actually, let's change it a bit higher. We'll go 100 MeV, just so it doesn't stop in the detector. In fact, let's be thorough and go back to our viz.mac, change this to 100 MeV, and just check that when the volume, if the electron exits our volume, then it doesn't crash or something. So let's just suppose we did our copy ID incorrectly, and when it exits volume, it might crash because it's trying to access something that doesn't exist. So let's just make sure that when we shoot a non-stopper, that it will actually work. So it didn't die, so I'll call that a success. So if we just up here, scroll down, PX5, and where's our last PX? Fizz PX here, and 2.9 there. So good. So ran, it didn't stop. So let's call that a win. So starting here, and we've got our what did we set up? Oh, we're in VisualMax, sorry. So 100 MB, so the beam will be 40 by 40, and let's shoot 100,000 particles. Oh, and let's just go back to our stepping action. Okay, we'll see how much output we get. I think I'm going to cancel. Oh, let's just start with 1,000. I'm just thinking about how much junk we'll get to the screen since we're still outputting every time the pixel gets a hit in it. So let's just run it now and see how we go. Okay, it wasn't too bad, but only 1,000 particles. So here we see we got quite a bit of dose for 1,000 particles, but again, these pixels are 5 centimeters thick, so not too unreasonable. But let's just go crazy high and we'll go with 10,000 particles, and let's just comment out these lines here. So now it's just going to run without talking to us. All right, so see fairly uniform energy deposition, which as we expect since we shooting a 40 by 40 centimeter beam, but let's just say we changed it slightly to be so how far? So 10 centimeters from the centers. So the end will be 15. So if I shoot 10 by 10, so if I shoot by 10 by 10, then only a quarter, well, yeah, a quarter of the far left, far right pixels and half of the other pixels. Hopefully you follow what I'm trying to say. All right, so that's what we're expecting. So in the center pixels, remember 4 is the center, should have the most. So let's just visualize this quickly. And so remember, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8. And so this copy ID 4. So, and we're shooting we're shooting a 10 by 10. My memory today. Yeah, a 20 by 20, so 10 from the center. So remember, it's 10 to 10 from the center. So we were shooting half of this volume and only a quarter of the edge quarters and half of this quarter, half, quarter, half, quarter. So remember, this is copy ID 0, so our 0 should have the least. So 2,000, and this should be about double that, so 4,000 we'll say, and then this should be again small, and then this is copy ID 3, so again a half-ish. Then center, since it's fully being irradiated, we get about twice than this bottom one, more or less, and same with all the other volumes. So this was more of a conceptual way of how to deal with the copy ID of multiple volumes. But as again, I showed you how to do it with stepping action, but in a real world simulation, you'd probably want to consider using the sensitive detector class instead of the stepping action class, since the sensitive detector is meant to be much more efficient when you're doing process like this, where you're getting the energy deposition and volume, but the concept is the same in terms of the commands. You're still going to be retrieving the copy ID. You get the edep and you add that to the tally, but yeah, so the concepts are the same, but if you actually do this, then you might be using a sensitive sensitive detector class instead of the stepping action. And particularly if you wanted like just the energy deposition for a certain track or an event. So this is just doing the accumulated or the total energy deposition over a total run. But let's say you wanted to know how much dose was being deposited per track or per particle. Again, you could do this in stepping action. You'd have to like do flags for tracks or something, and for events using like the primary particle ID, but you'd want to use again the sensitive detector class instead, since it's a bit more purpose made for that type of thing. But conceptually all the same, but that's just the basics of using replicated volumes, repeating volumes. And also one final thing, I showed you how to do this with just a for loop, and this is fine if you've only got like a few volumes or a few hundred or even 1,000 or so volumes. But if you're moving into like tens of thousands or hundreds of thousands of volumes and your volumes are equally placed, then you might want to look into replicated volumes, or word escapes me, but you might want to look in how to use replicated volumes. In fact, maybe I'll do a video sometime in the future, but that's that for now.